Rip, any plans to get back out into the field?
I mean, how can you plan for anything right now? We're hoping, I'm cautiously optimistic that we'll get out next spring. As I'll describe in a little bit, we have a missing season of data from March of 2020 that we'd love to fill in with March of 2022. So I have funding through my department to get out there. It's just a question of, is it safe for us and for everyone else involved?
Yeah.
What about you?
I've got all this backed up field work, so if I can, I may be out there 4 times in the next year.
Jeez, good luck.
Yeah.
Well, we really have to cross our fingers. So hopefully the new surge, new wave can turn around soon. But who knows?
Bangladesh just passed a peak and is going down. Is actually better than in the U.S. right now, and they're vaccinating like crazy. They just started vaccinating again.
Okay. I have a couple of friends from Western Coast. So
it's really up there.
Okay, so it's 9 a.m. Eastern Coast. Are you ready? Okay. Okay, good morning and good afternoon and good evening. So welcome again to this World River Delta System Source to Sink webinar series. Today we invite Dr. and Professor Rip Hale from ODU, so Old Dominion University, come here talk about the Granges-Brahmaputra and Magna Delta. So again, as you can see from the first slide, this new webinar series is sponsored and co-sponsored by National Science Foundation, North Carolina State University, and Louisiana State University in North America, and also in Europe, Utrecht University School of Geoscience, and in Asia, State Key Lab of Estuary and Coastal Research, East China Normal University. So all our including this talk, as you can see, this talk now is live on YouTube. If you go to our YouTube channel, you also can watch this talk, or you can, after even you miss any of talk, you can go back to rewatch and replay any archived recorded talk on our Source to Think YouTube channel. And if you want to follow up any update about this webinar series, you can follow us on Twitter, Source to Think. As you can see, you can follow us. We have 1,002 more than 200 people follow us. And for in the coming, as you can see, every Wednesday, all the way until December, we already lined up a bunch of good talks. As you can see, John Anderson, Xiaohua from Australia, Liu from Woods Hole, and Don Wright, and as you can see, Zhifei from Tongji. And so next week, we have our first speaker from Thailand. So she will come here talk about Trophea River Delta. I think these are the very interesting South Asia Delta systems, particularly under the impact of natural and anthropogenic. The shoreline retreat is very bad, very severe. So please mark your calendar, come here next week. And Rip is currently an assistant professor in Old Dominion University. As you can see here, he graduated originally from Brown University bachelor degree and University of Washington with master and PhD, particularly working on the small mountains river sediment transport from that very strong, very famous group. And then a postdoc at Vanderbilt, and now is assistant professor. His research mainly focused on the sediment transport process and the depositional product across the wider range, and from the submarine canyons, continental shelf, estuary, and the delta settings. So he mainly used acoustic optical sensor to have observation, understand the hydrodynamic process of the sediment. So I think now I will give floor to Rip. Rip, now you can share your screen.
Okay. All right, is that looking all right?
Yeah, good.
Okay, well, thank you for the introduction, Paul, and thank you everyone for joining this morning. This is such an amazing seminar series. I'm really happy to be able to share my research here with you this morning or evening or whatever time it is. This is research that is the result of about 5 years so far, 5 years and counting of work on the Ganges-Brahmaputra Delta. I'm going to be showing results that are the combined efforts of not just myself, but also collaborators and students, current and former. So a huge thank you to all my US and Bangladeshi collaborators on this project. And yeah, so specifically we'll be looking at transport and deposition processes on the GBM Delta, the Ganges-Brahmaputra Meghna Delta. This cover image kind of sets the stage where we've got a tidal channel to the left here, which blends seamlessly into a smoggy sky. There's the intertidal bank, which is a extremely muddy environment. And then to the right, we've got an inhabited area, which is protected by this low-lying embankment, also known as a polder. I should add, this research has been funded by the NSF, the Office of Naval Research, and done in collaboration with the World Bank and CRDF Global. So I'll give you an introduction to the region and why we're particularly excited and interested in studying sediment transport and deposition processes here. This is a heavily populated area. As a delta, it's inherently low-lying. And there have been some pretty major impacts associated with human modifications to this area. And we'll go into that in a little bit. My particular lens is sediment transport and deposition. So we're going to look at sediment availability, that is how much sediment is where and when, and understand how that sediment goes from the tidal channels where it's moving back and forth twice a day to onto the platform where it can be used to build up these low-lying regions. And then finally, we'll look at how things might change under future scenarios if there were to be a reduction in either freshwater or sediment delivery to this region, and what this means for the viability of the area. So to begin, I like this slide a lot. This is an estimated population density. This is from 2015, but the trends are similar. Warmer colors are more densely populated. So of the 7.5 billion people on Earth, about 40% live in just 4 countries: China, India, Pakistan, and Bangladesh. And the red here, this darkest, brightest red you can see, that's where Bangladesh is located. So Raleigh, North Carolina, hosting our seminar today, about 1,000 people per square kilometer. New York City, we get about 10 times that at 11,000 people per square kilometer. And then Dhaka, the capital of Bangladesh, has closer to 58,000 people per square kilometer. So a phenomenally dense population. To put it another way, the land area is about 156,000 square kilometer, and there are approximately 160 million people. So this is the equivalent of taking half of the US population and squeezing them into an area the size of either Louisiana or Iowa. And of those 160 million people, about 20 million people live in the Southwest region. Bangladesh is an interesting geological location. It makes up the top set of the modern Ganges-Brahmaputra Meghna Delta, and it's located at the junction of the Indian plate, the Asian plate, and the Sunda plate. So you have this collision margin, which is building the Himalayan mountains. I think previously, yeah, here's Mount Everest for reference. So that's the source of a lot of this sediment. And then it's carried to the ultimate sink, either in the delta or through the swatch of no ground here. There's also a subduction of the Indian plate under the Sunda plate on the eastern margin. So that creates some interesting tectonic setting for the enhanced subsidence we see here. As I mentioned, here comes the Brahmaputra in from the east, the Ganges coming in from the west, and they coalesce and join the Meghna River, ultimately bringing sediment into the Bay of Bengal. So by basin area, this is about 1.6 million kilometers, draining approximately 75% of the Himalayan range. The average water discharge of the combined Ganges-Brahmaputra Meghna River is 38,000 cubic meters per second. And collectively, this brings about they carry about 1 billion tons of sediment per year. Roughly 75% of this material makes it to the mouth of the GBM. And then through tidal processes, about 100 million tons is redistributed here to the Southwest Delta Plain. So where we're focusing today is right here under my pointer. And I just want to reiterate that the majority of the sediment that is arriving in this area is actually sourced from the mouth and worked back on shore as opposed to directly coming down the Garai River. I mentioned that the water discharge is on the order of 38,000 cubic meters per second, but as this figure shows, that's almost seldom the case. It's a strongly monsoonal discharge regime where we have low discharge during the dry season, summer months, or winter months, and high discharge during the wet season, summer months. And so we've got pronounced variability within a year as well as between years where we've got relative drought and flood controlled by the El Nino and La Nina respectively. So on the order of 60,000 cubic meters during an El Nino year and 120,000 cubic meters per second during a La Nina year. So as a result of this, the subsidence we've described and the variable discharge, flooding is just a fact of life in Bangladesh. So what this figure is showing, the shaded regions are areas of the country that were inundated at some point from 1999 to 2009. And the vertical, those are data from Irina Overeem, and the vertical yellow bars and the black dots are GPS-based subsidence rates and subsidence from tidal stations provided by Mike Steckler. And so what we can see here is that as you move to the south and east, where again, there's the subduction under the Sunda Plate on the eastern margin, we see enhanced relative subsidence. The land is going down faster, and there is flooding pervasive across much of the country. So what does that mean? Well, as a mechanism to combat some of this flooding and to increase agricultural output, the government sponsored a program to build polders, which again are earthen embankments, beginning in the 1960s and 70s. So outlined in this map here are the locations of the polders. There's about 5,000 kilometers of handmade levees, which generated approximately 9,000 square kilometers of farmable land. And so today's talk will be focused here at Polder 32 in the red box, or part of today's talk will be focused there. So dramatically increasing the agricultural output. Here's what it looks like from the ground. So we've got, again, the tidal channel on the left side here, that muddy intertidal bank. The picture is taken from the top of the polder wall. And then as we look here to the right, we've got freshwater storage. This picture was taken in late October or early November. So following the peak discharge of the wet season, but there's still ample fresh water in the area. The bottom image here shows another view of this from the tidal channel itself. And so we can see a reinforced polder in this case, but again, entirely handmade, hand constructed. Here's a couple more pictures of the polders on the ground. This is the same location at a high tide in the upper panel and a low tide on the bottom panel. You can see these two buildings have been abandoned as the channel has migrated and water has come up. You can see the high water mark on this brick building, for example. And so we've got in the foreground a relatively low embankment, and then behind that you can see a higher and more substantial embankment just peeking through. And if I were to return to the field tomorrow, there would be an even larger embankment behind this one, as recent support from the World Bank has generated a machine-constructed polder here. So we can see channel dynamics and rising water levels are threatening livelihoods already. So we'll look a little more closely now. This is the location of Polder 32. It's not just rising water that is a threat here. We've got, if we look at some detailed bathymetric data from inside this yellow box, this is provided by Mike Reed and Jim Best. So this is a pretty traditional point bar cut bank complex, and we can see these characteristic scallop shapes on the cut bank, which we interpret as submarine slumping. Basically, over erosion of the toe of the bank causes over steepening, and the bank fails dramatically. And as a result, we've got migration of this cut bank landward. So you can sort of see that in the pixelated satellite imagery underneath, where there's the remnants of a wall here, and then a much more substantial wall constructed behind that. So as this channel has migrated to the northwest, they've had to subsequently move their polder wall. It's not just migrating channels, it's also rising water. So these data from PETHIC and a report to the World Bank in 2012, we're looking at monthly mean water levels from two locations, one here at Khulna and one here at Mongla. And so these are basically tide gauge stations where they measure the mean water every month. The high frequency variability, that's the interannual, the monsoon variability from year to year. So high water during the monsoon, low water during the dry season. But then if you do a linear regression, you can see the high tides are getting higher and the low tides are getting lower. And that's true to a lesser extent at Mongla as well. So if you combine the various factors impacting the water level here, you have global eustatic sea level rise, you've got the delta subsidence, and you've got this tidal amplification. At Mongla, this results in an effective sea level rise rate of about 1.7 centimeters, excuse me, at Kulna, it's 1.7 centimeters per year, and at Mongla, it's closer to 1 centimeter per year. And I want you to keep this 1 centimeter per year rate in mind as we move forward. So here again is Polder 32 in the center of the screen. There's about 50,000 residents. It's a 50-kilometer embankment, 60 square kilometer area. Tide range during spring tides is about 5 meters here. And again, the primary sediment source is from the main stem GBM River. So sediment has been discharged into the Bay of Bengal and then reworked northward through the Shibsha River and the Fasur River. And inside the polder, behind the embankment, the average elevation sits about 1.5 meters below the mean high water level. This is contrasted with the Sundarbans National Forest, a portion of which you can see here in the dark green to the south. Here's a picture of the mangrove forest from the ground. It's a beautiful mangrove forest. It's a UNESCO World Heritage Site. It's the largest continuous mangrove stand in the world at over 10,000 square kilometers, home to Bengal tigers and Ganges dolphins and other charismatic megafauna. But most excitingly, as a geologist, this is keeping pace with the rate of local sea level rise. I would be remiss if I didn't share some of our charismatic megafauna here. So in the upper left, this is a tiger footprint or pug mark from fieldwork in October 19. They were inspecting the installation of a sediment elevation table. In the bottom left, here's their dinner. These are spotted deer in the Sundarbans. And you can see they are wading through the mangrove nematophores. And then on the right side, this is a I don't know, probably 4 or 5 meter saltwater crocodile that also wanted to see what a tide gauge installation looked like. So thankfully, we noticed the crocodile after we got out of the water, but certainly was an exciting day. So here's our a conceptual model of how the polders work and the downsides to that. So in a polder landscape, you are sequestering the tidal channel from the inhabited area. So the benefit is you can have year-round agriculture, you can control when the area you live is flooding, and in fact, it might only be by monsoon rains or other mechanisms of flooding the field. The downside is without a sediment supply, because of compaction, we have local subsidence, and without sediment supply, this results in a scenario where the accumulation rate is much lower than the rate of sea level rise. So high tide now sits 1.5 meters above your landscape. Yeah. This is contrasted by the Sundarbans, where there is no constructed embankment. And so as a result, the platform will flood to a depth of about 30 centimeters during spring tides around the year. And as a result of this continued connection between the delta plain and the tidal channel, we see accumulation rates that are more or less keeping pace with the rate of sea level rise, even that relatively fast effective sea level rise rate we described at 1 centimeter per year or more. This digital elevation model is a dramatic representation of that, although I have to add that a lot of these brightest colors are a result of the tree canopy, and we don't actually have an 8-meter disparity between the two locations. But if I asked you to outline the Sundarbans, I think that would be a relatively trivial exercise. I've taken the liberty of doing so now. So again, warm colors are the relatively higher Sundarbans area where there's a continued connection to the tidal channel. In these purples, this is the Polder region where the landscape is sitting 1.5 meters below mean sea level. And if we look at Polder 32 now, what we're looking at here is a series of elevation transects. This was done by Auerbach et al. In their paper 2015. In the background, we've got a representative spring neap tidal cycle, and then co-located in elevation are these elevation transects. So each series of dots is a different transect across Polder 32. On the left is the river terrace, so this is outside of the polder. Here's the top of the embankment, and then every 100 meters moving inland, we've got measurements. So mean high water is this black bar here. The green dash line, and so there's a companion transect to the Sundarbans in the black triangles, so that's this green dash line here. And then the red dash line is the average elevation behind the polder. And so what we're seeing is because the sediment supply to the polder landscape has been cut off by the polders, the result is a landscape that sits about 1.5 meters below mean high water. And this represents this poses the threat of prolonged inundation in the event of polder failure. So whereas the Sundarbans only floods during the highest tides throughout the year, if the polder were to fail, any one of these high tides could result in inundation. And that is a very real threat here. These are just a few images, a few headlines I grabbed from the Guardian website, but we're looking at an average of 2 to 3 cyclones per year impact this area, and any one of those cyclones could have incredibly detrimental effects in the form of polder collapse. And in fact, that is much of the motivation for the initial foray into this research. This is a Google Earth satellite image from October of 2008. Here we can see the tidal channel. So again, October would be towards the end of the monsoon season. Got the tidal channel, brown, silty water. We've got the verdant rice fields inside the polder growing away. In May of 2009, Cyclone Ayla made a direct impact on this region. And so now this satellite image from 2010 shows just what devastation was wrought, where you can basically not distinguish the tidal channel from the landscape. And that's a result of 5 embankment failures, 4 of which I'm highlighting in this image. And this picture was taken this image was collected 17 months after the storm struck. So here's what conditions would have looked like on the ground, where you can see everyone's living immediately on top of the polder to the best of their ability. And this would seriously impact their ability to grow rice or perform shrimp aquaculture. But this is not meant to be a story of devastation. Instead, I'd like to talk about the perseverance of the human landscape. You can see they've now reconstructed the polder at each one of the embankment breaks, including at the interior, which required 20 kilometers of new embankment because there was such a large volume that was being flushed. And then I've outlined in red a tidal splay deposit, which is where sediment was delivered to was delivered to this landscape during high tides because the polder was missing and there was a reconnection. So we can see this rapid sediment deposition in these tidal splays. Because of this daily inundation for more than 2 years, the result was 38 centimeters per year of deposition proximal to the breaches. So you can see this entire thickness of sediment was deposited in the 2 years that the polder was open after Cyclone Ayla. Here it's a 72 centimeter deposit. And so this represents the potential for rapid landscape recovery. So I put together, again, a conceptual model. If we could intentionally and in a controlled fashion breach the polder, this would present the opportunity for rapid sediment accumulation. And depending on your estimates, it would be a minimal interruption to the food supply. The downside, of course, is that there would be interruptions to the food supply during these periods of inundation. The sandy sediment that comes into the area during this sandy sediment you can see through here. This is not optimal for growing rice. And in fact, there's anecdotal stories of farmers digging out this new deposit to return to the finer grain material underneath. And this also doesn't prevent the future imbalance. As long as there is a polder, as long as you're restricting the ability of sediment to make it from the tidal channel to the field, this will be a pervasive problem. This also assumes that there isn't a change in the water or sediment supply to the area, and that might be a poor assumption. On the Indian side of the border, on the Granges-Brahmaputra, they're planning and have begun the construction of a national river linking project, which will, through a series of dams and diversions and canals, redirect water for agricultural interests in India. So as a result, the time period during which fresh water is delivered through the Ganges and Brahmaputra rivers would be reduced by about a month. And the sediment load, depending on which river and which estimate, could be anywhere from 10 to 75% reduction. And so this is work by Higgins et al. In 2018, and they predict delta-wide aggradation rate being reduced from 3.6 millimeters per year to 2.5 millimeters per year. So we're wondering, how will this impact the delta's viability? And so the key questions to consider as we move forward is, again, my lens is sediment transport. So how much sediment is in suspension in the tidal channels? And also, what are the seasonal and spatial patterns of this sediment availability? It's one thing to have it in the channel, but if that sediment can't make it from the channel to the platform, as we see in the case of the polders, it's not doing us very much good as far as landscape reconstruction. So using the natural area, the Sundarbans National Forest, as our laboratory, we want to understand what factors control sediment delivery to the platform. And so which should we focus on as far as when we're looking for restoration capability. And then finally, how might a reduction in this sediment supply or freshwater supply impact the delta aggregation? So let's look now at the sediment availability. And we'll look at this in a few different scales. So as part of this research, we collected a series of acoustic Doppler current profiler surveys. This is the mighty Mawali, our research vessel, typically a honeymoon cruiser, but does excellent work as an oceanographic research vessel. So we have two transects, one here to the south and one to the north. And between those transects, there is a single outlet into the Sundarbans here and another smaller outlet here. And basically, our idea was sediment and water that come through the south and don't make it out through the north must therefore be depositing, entering into the Sundarbans. So we collected these transects during spring and neap tides during both the dry and wet seasons in 2015-16, I think. And the initial goal was to estimate the discharge of sediment into the Sundarbans. And we weren't fully able to constrain the budget, but we made some strides. And to put the cart before the horse, what we saw was about 120,000 tons per day enter the Sundarbans during the monsoon spring tides. It's just this local region of the Sundarbans. And importantly, about twice this amount of material came through the south and then bypassed through the north. So there is a lot of sediment moving around in these tidal channels. Here's what those data look like on the right side of the screen. The purple triangle was collected near slack low tide here on March 21st. So the colors represent the velocity, and then I've just added the arrow showing that this is velocity into the board at this point. To compute discharge, you take the spatial integral of these velocities, and that results in this case, a near slack discharge of about 200 cubic meters per second. Just a couple hours later, on the early part of the flood, now we've got flooding velocities on the left side, still ebbing to the right. And what we're seeing is discharge on the order of 10,000 cubic meters per second. So the second component that we're interested if we're looking at sediment transport is suspended sediment concentration. And so these data were collected at the same time as the ADCP transect. So on each westbound transect, we would do a CTD cast. There were a variety of deployment strategies. My favorite remains a monkey wrench zip tied to an optical backscatter sensor. So we would do 2 to 3 casts per westbound transect. 2 to 12 meters would be the depth of the cast. We're really looking at the suspended, not the bed load sediment transport here. But again, it's that suspended load that we expect could be available to the platform. So that's what we're most interested in. The depth of the cast is constrained not just by the length of the rope, but also the fact that we would not infrequently see water velocities in excess of 4.5 meters per second. So it's hard to get anything to sink at those speeds. And what we can see in the middle column, where depth is the vertical axis and suspended sediment concentration is the horizontal, is that it's a generally well-mixed water column from a suspended sediment standpoint. So for each cast, I would take an average of these values, and then both casts on each transect would be average, and that would represent the channel-wide average suspended sediment concentration to compute a sediment flux. So we'll look at a few panels that are similar to this. The upper panel is the water pressure. So this is our tide stage. And for reference, on the right here, we can see in red, this is the portion of the spring neap tidal cycle that we're interested in. The second panel is water discharge. Third panel is suspended sediment concentration. So each of these survey days would last for as close to a full tidal cycle as we could reasonably perform. And so we see from a discharge standpoint, these are collected at the north transect here. From a discharge standpoint here, we're looking at plus or minus 20,000 cubic meters per second. And just as a reminder, the average water discharge of the Mississippi River in the modern day is about 16,000 cubic meters per second. And the suspended sediment concentrations, we can see in excess of 1.5 grams per liter, not infrequently. And again, this is during the dry season on this major channel. So we're seeing 20,000 cubic meters per second water discharge and concentrations in excess of a gram per liter, despite this being the dry season. Same location, now we've returned in the wet season. Again, tide range is about 4 meters during our sample day. Again, discharge is plus or minus 20,000 cubic meters per second. I should mention that flood values are on the bottom and ebb on the top. And then we're seeing suspended sediment concentrations now typically above a gram per liter, but from a peak value that we're seeing similar peak, and it's just that the average concentration during the monsoon is about 50% greater than during the dry season. And again, those are comparing spring tide to spring tide. Now let's look at the dry season, the wet season neap tides. Now we're looking at about a 2 meter tidal range. Discharge is closer to 10,000 cubic meters per second. And suspended sediment concentrations are dramatically lower with peaks around 0.5 grams per liter. So the water discharge is reduced by about 50% during these neap tides, and the concentration is reduced by 65% or more. So now we'll move from this major tidal channel into a secondary tidal channel, which connects the Shibsha River to the west with the Pasua River to the east. And the data, we're looking at a slightly different data set here. Now the vertical axis is the water pressure. This is the tidal stage basically. And the color bars correspond to suspended sediment concentrations. And I've highlighted the left side of this image as the wet season and the right side as the dry season. And really what I want to point out is that concentrations can be in excess of a gram per liter, and that these peak concentrations are observed primarily during the monsoon season. And so now let's go to the terminal tidal channels. These are the channels that work their way into the Sundarbans National Forest, and this is where much of the actual sediment is being delivered. And so as the teaser, we've just got a few values of average concentration across some casts during a few different tidal cycles. So we've got dry season spring tide here in the upper panel, and then 2 monsoon measurements, one during spring tides and one during neap tides. And I don't mean to suggest that these are, these averages that I'm displaying are the be all and end all. We're not looking at the same time periods, for example. What we can say is that during the dry season, the average concentration from our measurements was about 0.14 grams per liter, and that's during spring tides. Meanwhile, during the monsoon season spring tide, it's closer to 0.8 grams per liter, and during monsoon neap tides, it's closer to 0.4 grams per liter. And we can even see, if we just look, for example, at this falling limb here, these dark blue colors are darker than these light blue and green colors. So we can see that when we do compare apples to apples, there's more sediment in suspension during neap tides in the monsoon here than spring tides in the dry season. So as we go from the largest, those major channels, and the subsequently smaller channels, we see that in the major channel, the concentration is mostly controlled by spring neap variability. Seasonally, it's less dramatic. As we go into smaller and smaller channels, this seasonal variability increases. And so by the time we get to these terminal tidal channels, it's more of a seasonal control. And it's these terminal tidal channels that irrigate much of the Sundarbans National Forest interior. So this is where we want to maybe look at how sediment is being delivered to the platform. So we have estimates of deposition from a variety of methods. One particularly exciting one is the use of sediment elevation tables. This is work that's been spearheaded by Carol Wilson and her students from Louisiana State. So with SETs, you have a rod that's pounded into the ground, and then you periodically return and measure the height from the reference height from the top here to the top of the sediment. And this is compared to a marker horizon of some sort. So you can get the vertical accretion as well as the total elevation change. And typically measurements occur twice a year. In our case, it's during March and October. And so this allows us to understand net change on a seasonal basis. And so here's what those data look like. This is from Jeff Bomer's work published in 2020. The blue line is the total elevation change. So this is the SET measurement. The green line is the accretion on top of sediment tiles, which are deployed seasonally, and the dashed line is the accretion relative to the marker horizon. This dashed line should be interpreted with a huge grain of salt because there are crab burrows pervasive in this area. So we probably didn't actually see 20 centimeters of deposition during this time period. So if we just use the cumulative sediment deposition on sediment tiles, we see about 10 centimeters of new sediment and a 5 centimeter net elevation change. So obviously, and also that this is primarily occurring during the wet season. The sort of stair-step pattern that we see in that blue line is the elevation change that we're particularly interested in. So what we really want to know is what's happening between these sampling events. And what is controlling delivery of sediment from the channel to these platform environments. Here's just some pictures of what 2 centimeters of sediment looks like. This is a single monsoon season's accumulation. So here's the marker tile, and all of the sediment was deposited on top of that. In the second image here, we can see actually a mangrove nematophore has grown on top of the sediment tile. So not only has there been 3 centimeters of deposition, but there's also been enough time for this mangrove to grow its roots over top of the tile. So to really get at how is sediment going from the channel to the platform, we devised an experiment by which we would put every instrument in my lab in the water at the same time and see what happens. So basically, here I am in the field with my Bangladeshi colleagues, and we sit in our small boat for an entire tidal cycle while simultaneously measuring a variety of parameters. So the color of the sensor corresponds to the location it was collected. So light blue is at the channel surface, dark blue is at the channel bottom, purple is on the platform. And then we've also got pressure and temperature from a few other locations. But basically, we're measuring water level, temperature, suspended sediment concentration, water velocity, water salinity, with the goal of understanding which one of these factors is the most important in controlling sediment transport from the tidal channel to the platform. We're going to look through a few panels that are all quite similar. I realize this is a lot of data, so I'll take you through it. So right now we're looking at dry season data. We've got site 1, which is near this secondary channel, and site 2, which is near the end of the terminal channel. And we've got 4 panels. We have water level, suspended sediment concentration, current speed, and then this is data from the ADCP. This is another way of looking at water velocities. So again, the blues are collected in the channel, the purples are on the platform. And what we can see here, there's about a 4-meter tidal range. And you can't see it on this figure, but the inundation depth here was about 7 centimeters and lasted for about 1 to 2 hours, depending on location. And the suspended sediment concentration reduces as you move inland. And that's true both from site 1 to site 2. So if we look just in the channel values here, at site 1, we're looking at 600 milligrams per liter versus 200 milligrams per liter, as well as from the channel to the platform. So again, at site 1, we're looking at 600 milligrams per liter at either bottom or surface, and on the platform, it's closer to 100 or 200 milligrams per liter. And we see this weak covariance between velocity and suspended sediment concentration. We've got low velocity, low concentration, high velocity, high concentration. So this suggests there is some amount of local resuspension occurring. We'll contrast this now with processes during the wet season. Same location, same sensors. So now we can see in the upper panel, again, about a 4-meter tidal range. So we like to think we're comparing apples to apples. Inundation, now you might be able to see is this purple line. So the pressure sensor was inundated. It's about 40 centimeters at either site, and it lasts for about 4 to 5 hours. So much deeper inundation and much longer inundation. While we do see a reduction in concentration as you move inland, it's a lot less dramatic than during the dry season. So if you recall, during the dry season at site 1, we saw about 600 milligrams per liter on the platform and 200 milligrams per liter, 600 milligrams per liter at the water surface and 200 milligrams per liter on the platform. Now we can see that while the surface concentrations are higher, so too are the concentrations at the platform. And it's also true that we see similar surface concentrations at either site 1 or site 2, which is just to suggest that we've got more we have more sediment remaining in suspension here. And finally, the velocity and suspended sediment concentration are largely decoupled at this point. We see very little correlation between those properties. So looking at all the data now simultaneously, to compare, we've got inundation of 40 centimeters during the wet season here on the left, 7 centimeters during the dry season on the right. The duration of that inundation is longer in the wet season, 4 to 5 hours versus 1 to 2 hours. I haven't shown the data yet. They'll be on a following slide, but during the wet season here, I should comment that the water is completely fresh, 0 PSU salinity, whereas during the dry season, it's closer to 20 or so PSU. So we've got a big difference in the seasonal salinity. And one thing we know about fine-grained particles is that in the presence of saline water, you have enhanced aggregation. These small particles stick together because of their electrochemical properties. And as a result, these flocks form, or these aggregates form, and will be redeposited. Will have a faster settling velocity than the individual sediment grains. And so as a result, we expect that these would be redeposited within the tidal channel rather than evacuated to the flats. And so we can really see that if we look at the surface concentrations in the dry season, so the vertical lines I should have mentioned, this is when the platform inundates. And when we go to 0 velocity here in the dry season, this light blue line, which is the suspended sediment concentration at the water surface, goes to 0. Whereas during the wet season, it falls dramatically, but not nearly to 0. It goes down to maybe 400 milligrams per liter. And so what we think that this is salt-induced aggregation of particles. So the other thing we can do with these data is look at the concentration before slack water and after slack water. And we can, if we make the assumption that the difference in these two concentrations is sediment being deposited on the platform, we can then calculate a deposition rate. So we take the difference of this red line from the before slack and the red line of the after slack and extrapolate, and we see about 1.8 centimeters of deposition per monsoon season. So I put together another conceptual model. Here is our well-mixed water column at the moment that the platform is fully flooded and the velocity goes to 0. Because of these slack waters and the representative particle sizes, we think that settling would be noticeable by about 10 minutes of slack water. And then after 20 minutes, we would expect the full water column to have evacuated the sediment. And this would result, based on the initial concentration, in a deposit of about 0.1 millimeters thickness. We know that there's about 180 inundation events during an entire monsoon season. So we would expect then about 1.8 centimeters of deposition. And so we can look now again to the data from Jeff Boehmer's work, looking at, in this case, the vertical axis is accretion, sediment accretion from the SETs we previously described. The horizontal axis is the seasonal hydro period. So what is the total number of hours that a given location is inundated? And how does that compare to its deposition rate? Well, we can see this positive trend from Jeff's data, but if we take the seasonal hydro period of the location that we're describing, and the expected accretion based on Jeff's relationship is about 1.8 or 1.9 centimeters per monsoon season. And indeed, that's exactly where we are measuring as well. So it is certainly supports that our method is representative of the processes that are occurring. This final panel shows the salinity data that I referenced previously. So on top, these are tidal water elevations from the tidal channel, where the horizontal dashed line is the approximate platform elevation within the Sundarban. So when water levels are above this line, we expect inundation. The second panel is salinity in units of practical salinity unit. So we go from the wet season field work here. As we move into the dry season, we see increasing salinity. Unfortunately, there was biofouling of the sensor, so these data are should be probably not included, honestly. But then we redeployed a new sensor here, and we can see that salinity was up to 15 PSU by March of the dry season. And then the bottom panel is suspended sediment concentrations, where we see concentrations in excess of 1 gram per liter extending into into November. So while the peak of the monsoon season may have been in September, we've got elevated concentrations into November, and then as salinity creeps up and up and up, those concentrations fall, which again, it might suggest that you have aggregates that are remaining closer to the bed. So what we can see is that in every way, monsoon conditions are much more conducive to sediment deposition. Unfortunately, because inundation depth and duration and suspended sediment concentration and salinity all are covariant, we can't yet distinguish which particular factor is the most important. They are all important and they all change simultaneously. So I'll briefly describe a bit of our ongoing work. In October 2019, we collected a few days of monsoon, post-monsoon observations on the southern coast here in the red box in an area known as Katka. So it's a similar experiment to what I described in the vicinity of Polder 32. Our dry season measurements, we hope to go back in March of 2022 now. These question marks keep moving forward. What we hope most of all is that the world stays safe, and that our research can become a priority, whereas right now the priority is the health of of everyone. And the goal of this work on the southern coast was to test the scalability of our early results. So do the processes here reflect the entire delta? Probably not. And what else is important for delivering sediment from the channel to the platform as we look in other regions? So here on the southern coast, we expect there to be more storm impacts, as this is much closer to the landfall of the cyclones. The mangroves are an important buffer of the storm energy. We're also closer to the mouth of the Ganges-Brahmaputra River, which might change the timescales of the sediment delivery. And I'll just provide a small teaser of our results. So here on the left, we just looked at these data. These are from the vicinity of Polder 32. This was site 1, and from the last slides, and this was during the wet season. And on the right now, it's the same data, but from the southern coast, from the Katka site. So what we can see is, despite the fact that these were both collected during spring tides, the tidal range to the south is much smaller. Not surprising, because as you move inland, there's a funneling effect as the channels narrow. The concentrations within the channel, that's these blue values, are lower at the coast. So down here around 400 milligrams per liter versus 800 milligrams per liter. Concentrations on the platform, meanwhile, are actually similar, about 400 milligrams per liter in either case. Interestingly, there's a change in the dominant transport direction. I don't have direction indicated, but up here at this location, it's the rising tide where we see the fastest velocities. To the south, it's the falling tide where we see the fastest velocities. And so all I can say at this point is stay tuned for more updates as we continue to dig into these data. And finally, I wanted to talk briefly about what we can expect going forward. What will happen in the case of a reduction in either the freshwater or the sediment delivered to this region. So here again are the present day conditions. So the upper panel is water discharge. The dashed line is the combined discharge of the 3 major rivers. The green line is the Brahmaputra, the red is the Ganges, and the red is the Meghna. Excuse me, the blue is the Ganges, red is the Meghna. So we've got our peak discharge in sort of August, September area. The second panel is the suspended sediment concentrations near Polder 32. Peak in concentration is during that sort of September time, but again, we can see even into December elevated suspended sediment concentrations. And the bottom panel is cumulative platform inundation. So the cross marks in either case are the duration of platform inundation. In green is near the outside of this was site 1 near the outside of the forest, and purple is at site 2, which is closer to the center. So for each spring neap tidal period, I added the total amount of time that the platform is underwater, and then the solid line is the running average of that. And again, peak in inundation is occurring in sort of September, October. So peak discharge, peak concentration, peak inundation, all during the monsoon. Now, as a reminder, in response to the canals and diversions constructed as part of the National River Linking Project, we're expecting a water discharge reduction of 24% in the Ganges and 6% in the Brahmaputra, and a duration of that freshwater delivery will be shortened by a month or more. As far as the sediment load, the Ganges would experience a 40 to 75% reduction, the Brahmaputra a 10 to 25% reduction. So in total at the river mouth, this would be about a 14 to 18% reduction in the sediment load. At our field site, a 12% reduction in the total volume and a duration of monsoon conditions shortened by a month. Locally, again, at the mouth of the GB rivers, we'd expect a 14 to 18% reduction, but based on the amount of sediment that comes around the corner to our area, we expect this to be a 9 to 12% reduction in concentration. So let's look at what that means. Again, in the modern day, we calculate a 1.8 centimeter per monsoon season deposition rate. That's from our research near Polder 32. So if we take just this best case scenario of this, the 9% reduction in the local suspended sediment concentration, this would result in a 10% decrease in deposition rate for a total of 1.6 centimeters per monsoon season. If we take just this maximum estimate of 12% reduction, now we're looking at 1.4 centimeters per monsoon season. Or the worst case scenario, this maximum reduction in concentration, as well as a month shorter time period of these freshwater conditions. And now we're looking at a deposition rate of 0.95 centimeters per monsoon season. And I'll remind you, the local effective sea level rise rate here is about a centimeter per year. So in this worst case scenario situation, we would be looking at a potentially devastating loss of land in the face of less water and more saline water. So to return to our initial questions and wrap up the talk today, how much sediment is in suspension in the tidal channels? Importantly, there is more than enough based on our calculations to at present values to nourish both the Sundarbans National Forest and to restore the elevations in the Polder regions. I'll remind you that whereas 120,000 tons per day are entering the Sundarbans in the vicinity of Polder 32 during those monsoon spring tides, it's nearly double this amount that bypasses to the north. So there is a lot of sediment still available. As you go from the largest channels to the smallest channels, the seasonal variability increases. So in the big channels, there's a tidal control on the suspended sediment concentration more so than seasonal. And we do see a general reduction in the concentration as we go from the largest channels, the Shibcha and the Pasur, to those smaller channels. And so this just is important to consider as we're thinking of where we want to monitor and how, making sure that we're accurately portraying the channels that are doing the most work to deliver sediment to the interior. Which specific factors control sediment delivery to the platform? Tough to say because they're covariant and interdependent. So we know that they all are important. And it's this salinity one that I don't know that it was a surprise, but it certainly appears to be particularly important, where when we think back to what we're seeing in the largest channels, concentration is similar during the monsoon and dry season. However, if that suspended sediment can't make it from the largest channels to the smallest channels because of the enhanced settling, then it's of little use in terms of land reconstruction. And finally, how might a reduction in the sediment or water supply impact delta aggregation? Like I just described, in the worst case scenario, even the natural areas will have a challenge keeping up with the locally elevated pace of sea level rise. And so it's not necessarily a lack of sediment as much as a lack of time during which that sediment is available. So with that, I will say thank you, Donabad, and I'm happy to take any questions.
Great, this is fantastic. Thank you, Rip. Let's see any questions from audience. If you have any question, just raise your hand or just unmute yourself. Go ahead to directly ask Rip.
Hey, Rip.
Anna, you have a question?
Hi. Great talk.
Hi.
Thank you.
Worth getting up at 6 a.m. for. I had a question about the flocculation. I feel like there's been a lot of recent interest in sort of like what generates flocks during purely fresh conditions and how much organic matter might be incorporated into flocks during either of those seasons. And I'm just curious if you have any ideas about sort of like flock size and organic matter that's being imported into the forest and sort of like how that might affect polder breaching in terms of like the quality of sediment that's deposited depending on the breach.
That's a really great question. At this point, our understanding of the flocks is largely speculative and based on, I won't be able to get back there, based on the fact that the surface waters go to zero during the dry season and not during the wet season. Unfortunately, because of these concentrations, a lot of the traditional tools that we would use to measure flock size, like a list, for example, are not available to us. So in situ observation of those flocks is going to be challenging. I've talked with the group at Dalhousie about using the PICS method. Unfortunately, we collected our we filtered our concentrate, our sediment onto glass fiber filters rather than nitrocellulose. So they can't do anything with those filters at this point. If and when we get back, I would love to provide them specific samples to look at. So yeah, it's speculative in that we don't have actual measurements of flock size. And the only other thing I can add is that the amount of organic carbon that's stored in the sediment is remarkably low. That's not to say that there's not organic material binding during either season, but what's actually preserved is really, really low. And that's probably because with a 5-meter tidal range and a lot of crab burrowing, things are just oxidized continually and there's not much opportunity for storage. But yeah, that's a really great question, and it's obviously important here, so we definitely need to dig into that going forward.
Awesome. Thanks.
So Hugh.
Yeah, Rip. Sorry, I'm just getting my video on there. Rip, really enjoyed that. I guess my question is, when I look at these numbers that you've got up now, I'm wondering to myself, just how buffered are we from the sort of catastrophic reduction in sediment loss that Higgins et al. Would predict? And so how much that sediment, basically how long does that sediment signal take to come from the mountains, do you think, down here? And should we worry about it at the moment? But obviously the water signal is going to be more immediate, and we can understand what that will be. So I'm wondering if we can understand the relative roles of the sediment versus the water reduction.
That's a really great question. Thank you. And we've looked into that to a small extent with one of my master's students. I'll see if I have any of her slides. We collected sediment cores from the lowest portion of the intertidal. This is work that is in revision right now. Callie Brown is part of her master's project. So what we were looking at specifically is understanding, so here's on the center panel, here's a sediment X radiograph, and on the right is just the median grain size. What we wanted to see was what is the depth of seasonal resuspension of material in the tidal channel itself, and could that be viewed as a source of sediment? And in short, the answer is yes, this material is frequently reworked. So there is definitely the capacity for a buffer as far as the sediment supply. The question becomes, what is the duration of that? But also importantly, like you were saying, if the freshwater is the challenge, that will be a more immediate signal. So that's definitely something that we're interested in and excited about, and look for this work hopefully soon. I think we might be overdue for returning our proofs, but we'll get them in soon.
Great.
I see a question in the chat from Ali Hassan Nishat. The reason that I only have data from the Bangladesh is because that's where I conducted my work. In the future, I would love to extend this research to the entire Sundarban. So I've been working sort of in this portion, but something like 40% of the Sundarbans is on the Indian side of the border. So I would love to extend this research to the west. Obviously, we don't expect these conditions to be the case everywhere. And so we've begun our spatial, improving our spatial understanding by going from here in the north to the south. And then in the future, I would love to work further and further west. So if you would, if you have any collaborators in India who'd be interested in working on this, by all means, please reach out.
Okay, cool. Dr. Assalam.
Hello, good evening from Bangladesh. I'm speaking from Bangladesh. I'm Professor Shahidul Islam of Dhaka University. I used to present in most of the seminar talk, weekly seminar talk, but I never participate in the discussion. But today I'm joining the discussion because you are dealing with the problem what we are now facing. So I'm giving some input from our side. It could be a little bit discussion, and at the same time some question. I know I have seen some of your publication. I have gone through those. And some of your collaborators, your co-authors are here today. I can see the Stephen Godbrit is here, and Michael Stackler is here. I think you have worked with them. Your team is here today. I'm a little bit concerned about few points you have raised. One concern is the sea level change. Whenever we talk about sea level, we use the term sea level rise. I little bit differ, I should say sea level change. Anyway, whenever we talk about the case of Bangladesh, it means sea level rise, rapid rise, and inundation, and lots of problems. And you have given some reference that sea level rise is more than 1 centimeter per year. That is the figure. And if you see the literature carefully published within this area, not throughout the Bangladesh or not throughout the coastal area of Bangladesh, just particularly in the southwestern part of the country, we can see the sea level scenario projected by the different authors is different. It varies from less than 1 millimeter to more than 1 centimeter per year. And some of the author, particularly I can mention the Morner. If you see the literature of Morner, he's now late. He has suggested that even sea level is falling here. And there are lots of field evidence that particularly the evidence of erosion in the coastal, in the Sundarban area indicate the sea level fall. So I'm not going into that controversy. What I am suggesting, what I am saying, you have noticed sea level rise of more than 1 centimeter per year, and that is actually as amplified tidal range. And if you go to the northern part of the Sundarban, that is the highly populated area and been largely interrupted by the human interference, particularly coastal embankments, settlements, bouldering, other things. And you have amplified the tidal range, nearly double, triple. And if you compare the tidal range of the southern part of Sundarban and the northern part, Mongla and area, you study area, it is nearly 4 times higher or double. In that case, what we are projecting 1 millimeter or 1 centimeter sea level rise, that is a misleading. That is actually amplified tide level, and that is being done particularly by the intervention of the human intervention. And if that is the case, if human intervention is the case, now you are again suggesting you have give a comparison that in open system, what is the tidal range, what is the sedimentation rate, and in a closed system, what is the tidal range and how is the sedimentation rate. And that is very clear that Polder has a very precise and very clear impact on the tidal range. So human intervention is a major cause. And at the same time, if you have clearly shown that tide is playing the key role in the sediment dynamics, sediment reworking, and the tide is amplified by the human intervention. So I can suggest it is not the natural process. It is the human intervention that is amplifying, that is making the interruption or a spatial variation. And if you see, the variation is more higher in the northern part of the Sundarban than the southern part of Sundarban. If that is the logic, and you are again projecting that if Indian river linking project is implemented in future, what would be the scenario of the southern part of Bangladesh, and what would be the scenario of the entire country and the entire delta as well? Now, my specific question is, that is the future scenario, but what already has been done because of the installation or installation of Farakka barrage in the upstream. There are 2 barrages, Farakka barrage and Gajaldova barrage in the upstream, which has seized the sedimentation or supply of sedimentation nearly 1/3. It was 3 billion ton per year. If we see the pre-Farakka time, the annual sedimentation supply in the GBM delta was 3 billion. Now that has come down to 1 billion. That is 1/3. And the second is the spatial temporal variation is changed, because during the lean time, the winter time, the entire sedimentation process is stopped from the upstream. But in this monsoon time, that is the signature you got, the impact of monsoon in the sediment dynamics, because in the monsoon time, the huge volumes of water comes from the upstream. And that is another major intervention in the upstream that has impacted the lower riparian country, So have you noticed such a tremendous impact of the upstream intervention in the sediment dynamics in the southwestern coastal belt of Bangladesh? Thank you. So, and thank you, Paul, for nice series talk. You have requested me to join. Definitely, I will join, but give me a little time. Thank you very much.
Yeah, please make sure contributor talk also. Okay, thank you. Okay, Rick.
Yeah, so Dr. Assalam, first of all, thank you very much for your questions and your comments. I appreciate all of that. So I tried to take notes so that I could respond to them. With the question of Munir's work and sea level fall, I think that is, I would disagree with some of his observations as far as what is sea level change versus what are deltaic processes. And so the erosion that he's describing, I don't think is evidence of sea level fall. I think that's a different process, but we'll set that aside. The rate that I'm using of 1 to 1.7 centimeters per year, that's from the literature described as the effective sea level rise rate. And so ultimately, you're absolutely correct. That is tidal amplification as a result of the poldering. So the energy of the tide is no longer attenuated by flooding the landscape. It's focused and has to continue to the north. So the term effective sea level rise rate, at the end of the day, since it is those highest tides that are doing the flooding, even though it's not actually sea level rise, it's the effective water is coming up. And so that might be just a term that is misrepresentative. So I apologize for any confusion. As far as the, you described that tides on the southern coast are lower, and that is absolutely the case. We can see those from our data. And we think what's happening here is, in fact, a lot of the delta is, a lot of the sediment delivery might be occurring during the cyclones when you have a massive influx in a very short period of time. We haven't been able to monitor that just yet. And as far as the sediment reduction in response to the construction of the Faraka Barrage, so there is some suggestion, for example, that the Garai River, which is, as I'm sure you know, is an offshoot of the Ganges. It's about 10% of the total Ganges discharge. The mouth of the entrance of the Garai now requires dredging in order to stay open, and there is suggestion that that is partially a response to the reduction in water and sediment that has been delivered as a result of the Faraka Barrage. But to the previous question about the lag time between the construction of a dam and when you see those impacts downstream, there's suggestion from, there's work done in the US on the Brazos, the Trinity, the Mississippi River by Jeff Nitrauer and his group, which shows that downstream of a dam, if the water supply doesn't change dramatically, you can still resuspend sediment that was stored in the bed and deliver that material to the coastline. So absolutely, in the case of Bangladesh, we're looking at several hundred kilometers of potential sediment source that could be brought in. As far as the changes, the anthropogenic changes in response to poldering, I meant to mention, Carol Wilson has a few really wonderful papers looking at things like channel infilling, charland creation as a result of the reworking of the hydrodynamics. Her calculation is a dramatic reduction in the overall tidal prism. So despite the tidal amplification, you have a simultaneous reduction in the total volume, reduction in the tidal prism, and that's resulting in deposition in some locations as opposed to, and erosion in other locations. So certainly there have been several disasters in the Sundarbans associated with coal or oil tankers running aground, and that's a result of the channel infilling. So absolutely, a large part of this challenge is local change or change to the system, both locally and globally. And I also want to take the opportunity to say that we have now two very small areas where we're making our observations. And I don't mean to suggest that this is our complete understanding of the Delta. Much more work has been done and should be done in the future. But this is certainly cause for consideration, if nothing else. But again, thank you for your questions.
Okay, cool. Thank you, Rip. So I think we give the last opportunity to Mike. Mike, you want to make comments, question?
Yeah, I was just going to add a little bit in that I think the Pethick and Offord paper showing the tidal amplification, if you look closely, it looks to me like there was a tidal amplification, following the polarization that went on for a number of decades, but that may be flattening out, so that the effective rate of sea level rise now may not be quite as large, that the river system has adjusted to the polarization enough that rise is not as large. Now there is still, quite a bit of there's still sea level rise in the land subsidence. We have a GPS on Polder 32 that shows about 5 millimeters a year of subsidence. So there's the sea level rise, whether or not there's tidal amplification, and then land subsidence. So it's still quite a substantial amount of relative sea level rise.
Yeah, that's an important point about the that rate of effective sea level rise flattening out from the amplification standpoint. There's not the polders are not expanding an area at this point, so there shouldn't be a continued constriction, basically. So you would expect that if it is indeed a response to polarization, you would expect that rate to flatten.
Yeah.
Sorry, one more point. Sorry, can I join, please?
Okay, we run out of time. Quickly, briefly.
One more thing is that, it's clear that the impact of polder on the local tidal range is clear, but you might be aware, but because you are following it up and you are coming again, you might be aware that government is going to implement a, delta plan 2100, 2100. It is a 100 years plan, and that is the repetition of the same thing in a large scale. If that happens, what will be the scenario in future in the entire area? What do you think?
I think I would need to spend a lot more time looking at the details before I can provide a solid explanation. But that's a great question. Thank you.
Yeah.
Okay. So I think in the last thing I want to make a comments. What we observed recently in recent years in South Asia deltas, including Mekong, Chofia River, Irrawaddy, and the Ganges, the subsidence rate can up to 10 millimeter per year, up to. And on average, many of those deltas is about 4 to 5 millimeters per year. So if you add a sea level, another 3 to 4 millimeter or 4 to 5, this almost have almost 1 centimeters, relatively change. And that should be a big challenge for those lowland delta area in South Asia. And particularly in this delta, we have an active fault. And so that's where we make the situation even worse, similar as the Irrawaddy Delta. So I think, that's a fantastic, I think a discussion is more interesting and we need this. Thank you, Rib. Thank you, all the audience. And so once again, next Wednesday, we will talk about Chofia River. This is just like a brother sister deltas in the South Asia, the Granges-Brahmaputra, Irrawaddy, Mekong, and Chofia River. So this is the first talk. We'll talk about Chofia River Delta. So please mark your calendar, come back next Wednesday. Okay, thank you very much.
Thank you.
Okay. So, Mr. But someone, are you